everyone, Katrina here, and today we're going to talk about dot product. Make sure to subscribe for more videos like this and watch to the end to see all the examples unfold. So dot product is part of my vector series. It's a really important application or understanding that we all have to know for vectors because it has a lot of really cool properties, and it's actually not that hard to calculate at all. So we're going to be looking at dot product right now in 2 dimensions. So we're still talking about 2-dimensional Cartesian vectors. So say we have these 2 vectors over here. We have vector u that I have highlighted in blue over here, and then we also have vector v that I have highlighted over here. So whenever we take the dot product between 2 vectors, it's very important that the vectors absolutely must be aligned tail to tail. So we can see that in this case they are. So they'll have to be aligned tail to tail. So just as a little recap, this is the tail of the vectors, and this part over here is the head of the vectors. So again, for this to work, the vectors are aligned tail to tail, and then we have this angle theta that exists between our 2 vectors. And that's going to be very important for this calculation. So again, u and v are any 2 vectors, and we have theta as the angle between them. And now we're going to learn one of the equations we can use to solve for the dot product. So just know there's a couple different definitions. So we're going to start with one first. And you basically use whichever definition you have the required information in order to solve it. So let's start. So we have that u dot v. We'll just zoom out a little bit there. So u dot v, so that's how you write the dot product, is simply just a dot. So this dot over here represents the dot product, exactly what its name makes it sound like, and this equals to the absolute value of u times the absolute value of v, and then you multiply that all by the cosine of the theta. And remember, this is the angle between it. And the absolute value signs, these are the magnitudes, if you remember vector lingo. So this is the magnitude of the vectors, which equals their size. And if you remember the definition, if you have some vector x, y, the magnitude, we'll call this vector a, for example, the magnitude of a would equal to the square root x squared plus y squared. Just so we have all the information we need. And again, this theta is between the vectors u and v. Okay, so what is the result of the dot product? So that's very important to note. So the result of the dot product is a scalar value. So it's also sometimes referred to as the scalar product. That's just like another name for dot product because the result is scalar. And remember from our intro to vectors that scalar values are magnitude, not direction. So they only give you a size. So that means the result of a dot product is not a vector. So that's very important because you can only add vectors with vectors. So if you take the result of a dot product, you end up with a scalar, then you can no longer add that with a vector. So that kind of comes into play when we're thinking about longer vector equations that we're trying to solve. Okay, so that is one definition that we have right there. So let's go through an example where we can use this information. Okay, so in our example today, we are trying to find the dot product with u and v, and we're given the following information. We have that the magnitude of u equals to 3, the magnitude of v equals to 4, and we have that theta equals to 30 degrees. So let's go ahead and use this formula. So like I mentioned, we use the formula that we have the information for. So here we're given magnitude of u, magnitude of v, and theta. And we have all those components in this equation. We're able to fill it in. So that means we can right away just go ahead and use this equation. So that's actually very, very nice for us here. So let's go ahead. U dot v equals to magnitude of u times magnitude of v cos theta. So magnitude of u equals to 3, magnitude of v is 4, and then we want cos of 30 degrees. So 3 times 4 equals to 12 cos 30. Now I challenge you, let's use our special triangles to solve for this. So we have, let's go ahead and draw that out. So we know that we have 30 degrees. So which special triangle is that? Across from 30 degrees, and we can have a right angle, obviously. So across from 30, we'll have 1. Across from our 60 degrees, we'll have root 3. And then our hypotenuse is going to be 2. So cosine, cos theta, equals to x over r, which is also known as your adjacent over your hypotenuse, depending on which lingo you like to use. So here our x is going to be root 3. So we got root 3 over 2. So that means that cos 30 equals to root 3 over 2. I'm always encouraging everyone to use their special triangles. So try not to grab or reach for your calculator right away, especially when you see angles such as 30, 60, 45, and 90, because you know that these are angles that we use for our special triangle. So that means our answer is 12 times root 3 over 2. We can simplify this by canceling out the 2 and dividing the 12 by 2, which gives us 6. So therefore, our final answer here is 6 times root 3, which cannot be simplified any further. And again, we note that this is a scalar quantity. It's no longer a vector. It is only a magnitude with no direction. Okay, so I'm going to tell you a little bit more about dot product. There's another definition, and we're going to go through some properties actually. So let's go through some properties right now. Properties. Nice. So this is one property that actually comes directly from its equation. So if we have our vectors u and our vectors v, right? So if u and v are perpendicular, so I'm using this sign here for perpendicular, so that means they're 90 degrees from each other. So u and v are perpendicular. If and only if, again, this double IFF, this means if and only if. So u and v are perpendicular if and only if u dot v equals to 0 for any non-zero vectors. Okay, so let's kind of break this down. So if and only if means it goes both ways. Means the statement, instead of a one-way arrow, it's a two-way arrow. So that can read as if u and v are perpendicular, then their dot product is 0, and on vice versa, it also reads that if the dot product is 0, then u and v are perpendicular for any non-zero vectors. And that makes sense. Let's consider the equation, right? We have that u dot v equals absolute value or magnitude of u, magnitude of v, cos theta. Okay, what if theta equals to 90 degrees? Let's look at our cosine plot. We've got 0, we've got 90, got 180, 270, and then 360. At 90 degrees, our cos function is what? It's equal to 0. So if cos is equal to 0, that means our whole dot product goes away and is equal to 0. So that makes a lot of sense. So if our vectors are perpendicular, if they're orthogonal, meaning the angle between them is 90 degrees, that means the value of cosine at 90 is 0, which means that our dot product is going to be 0. So that's a really important property for vectors. Let's do a lot of exclamation marks there, because lots of times as you move forward in vectors, you're trying to determine whether your vectors are orthogonal. And it's a really quick, easy test to determine if they're orthogonal if you take the dot product and you get that it's 0. Okay, so that's kind of a big fun property. Let's move on and look at some others. So this kind of just shows some of their, I guess, like distributive properties. So if we have in scalar multiples, so some scalar multiple k, and then we have u dot v, we can distribute, or more associative, so we can associate it as ku dot v, which also equals to u dot kv, and then we also have this distributive property that u dot v plus w equals to u dot v plus u dot w. So these are kind of two key properties to know. A few other things that we can just write out here is if you have a vector dotting itself, that's the same thing as its magnitude square. We also know that the unit vector is I, so I dot I, this is the x unit vector, equals to 1, and then the y unit vector j dot itself is equal to 1, and I and j are perpendicular, one's x, one's y, so that tells us that I dot j will equal to 0. Okay, so I'm going to show you one more formula. So we have our main one up here, which we already talked about in black. And now we're going to look at one more, which you can use if you don't have an angle. So this is considered the dot product of Cartesian vectors. So let's just write that for complete. So dot product of Cartesian vectors. Again, so you use this when you don't have an angle. So like I said previously, you use whatever definition that you have the information for. So here, if you don't have an angle, we're going to use it. So it is written as, so we have u dot v, and let's say that u is comprised of u1, u2, that's its ordered pair, and v is comprised of v1, v2, that's its ordered pair broken into components. Then we would have, then we write this vector out as u1 times v1 plus u2 times v2, and that's it. You literally just multiply the x components together, and then you multiply the y components together, and then you add them up, and that's all you have to do. So if we do a quick easy example of this, say we have u equals to 2, 1, and we have that v equals to let's say 3, 4. How are we going to do this? U dot v is going to equal to, remember, we're going to do u1, v1 multiply together. So that will give us 2 times 3. And then we add our y components together here, which is our 1 and our 4 over here. So then we just have 1 times 4. So this gives us 6 plus 4, which equals to 10. So that's really great. And remember, this again is a scalar. This is a great way when we, great way to find the dot product when we don't have the angle and we're just simply given two Cartesian vectors. It's very quick to solve, and this is an example in 2 dimensions, and we can extend the same example into 3 dimensions, 4 dimensions. You would just kind of imagine you have more terms over here. You would just keep adding, multiplying and adding each one as you go along. Again, so this completes our tutorial today on dot product. I hope you enjoyed it. If you did, please drop it a like and comment any questions that you have. Stay tuned for more vector videos. They will be coming your way, and subscribe for more videos. I'll see you next time.